Victoria, thank you. It's what happens when I rush in at the last minute. So yeah, the reactions are our bread and butter, our heart and soul. It's the main thing we focus on. And so I gave you less help as to which reactions might be covered. So your focus on reaction should be on the current chapters, but any reaction from previous chapters are fair game, and there are certainly some there. In fact, intentionally, did I put it on here? Oh, right here at the bottom. There are a few questions based on questions exam too, so I'm repeating some things. Now, doesn't mean it's the exact same question. It's repeating the topic. In my mind, comparable difficulty, but it will ask about things that, I was just more disappointed on in the last exam, generally what makes the grade. Okay, Rua?
Hi, I also have a few questions. For the EAS reactions, can you explain slides 40 and 41? I don't really understand it based on the commentary.
Oh, that whole chapter is on this, and I'm sorry, I misspoke. I have been so busy lately. Slides. Aromatic substitution. So yeah, this is a main chapter on the slide. So so which number?
40 and 41.
Okay, this one?
Yeah, and the one after that.
Yeah, because sometimes we end up with different numbers. First off, do not assume that I'm talking about reversible reactions for electrophilic aromatic substitution unless I say I want the thermodynamic product. So we're not really talking about mechanism here. It's just another example of doing the fastest reaction and making the most stable product. And when there's a difference, it has to be reversible. Okay, so I've made a slight modification to the slide. Under normal conditions, you get ortho and para with a tiny trace of meta. Okay, but if you force the reaction, heat it, beat it to death, now you get meta as the major product. Okay, so the normal product in all electrophilic aromatic substitution is a kinetic product, but these things can be forced to equilibrate. And I don't expect you to explain why meta is the major product, but all the carbons get some benefit from the electron donation of the alpha groups when they're meta to each other, not when they're ortho and para. So that's an explanation for those that really like to have one. Okay.
Is that really quick? Is that true for any type of substitution reaction, or is it just
No,
alpha
I don't know about all the others and whether they can be done in a reversible mode.
Gotcha.
So this is a somewhat of a passing example. This is a little bit more common, but still not that common. But the reason to show this is to talk about the structural differences that lead to it. And so, let's see, not as big as I'd like. Here, I'll help. So if you attack alpha, this is upside down, but that shouldn't bother you at this point. You get this allylic cation that also has resonance into the left-hand aromatic ring. Beta attack gives you an isolated cation that is isolated from this double bond. It can resonate with this double bond, but only at the cost of the aromatic ring. These two structures have the same number of resonance structures total, but the one on the left has the better ones. It has two without disturbing the intact benzene ring on the left. The other only has one. So that explains kinetic. And the thermodynamic is a little harder to see. You just have to accept that right here, that's a little crowded. This has more room. It's not even easy to see from models, but that's what the data tells us. Okay. Okay, so, some reactions can be manipulated to make either a kinetic or thermodynamic product. We've seen more than one example now. We'll see more in our last chapter. So it's a routine enough thing to see to give you multiple examples. Does that help?
Yeah, but for the slide, 2 slides before this one, the structure on the bottom left, can you explain what that is? That reversible?
This means if you take this line means that ethyl group is someplace on the ring. It's a way to show generic substitution. So what it means it needs to be decided in context, and I've said here ortho, meta, or para. So if you isolate the 3 pure diethyl benzenes and take each one in turn and treat them harshly, you get the same ratio of 3 compounds. And that is the strongest data you can have for saying that I got the thermodynamic product. The ratio is as far as I can push it. Okay?
Okay, and then when we're giving the products on the exam, because I know we said that unless the substituents added are tert-butyl or sulfonic acid or bigger, we don't have to worry about major or minor with ortho and para. But here,
well, no, here's a little different situation. I'm choosing to label it according to this data, but you're not expected to ever predict major and minor ortho and para. Just in one breath, the major product is a mixture of ortho and para, except for the 2 that you rightfully refer to.
Okay, thank you.
Yeah, so this is an isolated slide where I chose to be more specific. But predicting it is not easy, so we don't do it. Okay, Will Beasley, you had your hand
Hey,
up.
yeah, so I've seen that when you treat like a nitrile with an acid, I've seen a couple examples where it turns into an amide and a couple examples where it turns into a carboxy. What's the determining factor there?
We are not going to worry about that on this exam. You don't need to know it. Just accept that
Okay.
you can add water to it. That gives the
Yeah.
amide, or you can cleave that with water. That's the next chapter. And the first step is easy. The second step is hard. So you'll learn that in the next chapter.
All right, thank you.
Amides are rock stable. You got to beat on them. I knew a project in graduate school that had to be redesigned. Well, no, they didn't redesign that one. He tried for a couple of months before he was able to hydrolyze an amide to the carboxylic acid without destroying the rest of the molecule. So they are truly a stable functional group. Yeah, I got a question here in the chat. The rule on an exam is all you need to do is show me the major product, but when it's electrophilic aromatic substitution in a simple system, ortho para together are the major product. It's too hard to predict the ratios, which one is going to dominate. Okay, Sylvia, you up again?
Yeah, I was confused about slide 57. Also in the EAS PowerPoint.
57. Okay.
Yeah, I was.
Bromine and chlorine are just a convenient example here. This is meant to be more generic. They are orthopair directing, but we want to meta to each other. So you can't really do that directly without a terrible purification problem and a low yield. So the trick is to start, I've chosen to start with bromine on the ring. You nitrate it, that's going to go para, that's fine. And then you reduce that to aniline, and now the aniline is much, much more strongly directing than the bromine. So you can take that and chlorinate it. You're probably going to make the amide chlorinate it, then cleave the amide. And then you've got to get rid of the aniline nitrogen when you're done with it. So you do diazotization and then reduce it with a hypophosphorus acid. So did I? Yeah, I didn't spell this out, but you can write out the entire pathway if you want to. So
Okay, yeah,
it's
I
a
was
lot more steps, but will save you a lot of headaches.
Okay, thank you.
Yeah, this aromatic chemistry is age old. Let's see, Gregory again?
Yeah, my question is, can you reduce or get rid of aniline any way other than through diazonium salt?
Not that I'm aware of.
Got it.
That's the standard, tried and true way of doing it. You know, there's fancy ways to do almost anything. Let me show you something from here if I can find it. Well, it's easier this way. Oh, this is in the most recent version of my slides. Okay. Well, they'll do for today. Yeah, I found a method to directly reduce a carboxylic acid to an aldehyde. I'd always intended to find one. It's quite the challenging reaction. Yeah, I don't know where I have my most recent slides.
Can I ask another question?
Absolutely.
So in regards to the question that has to do with mechanism of acetals, will it be specifically about acetals? Am I saying it
I
correct?
give you no more information than what's on there, so don't ask questions about it. Come knowing the mechanism for making acetals well, and then see what you can do with the question.
Okay, then acetals is not the same as imines, right?
No, acetals have 2 oxygens.
Okay, got it. Thanks.
Yeah, and ketals go in the same breath. Here it is, I found it in this set. So I was curious, and this uses nickel chloride, zinc. This is a fancy pyridine ligand. It uses silicon hydrides. That would be the actual reducing agent. It uses this DMDC. I didn't look what that is. I'm not familiar with. And lutidine is another pyridine. And they make the witch's brew together, and it works in good yields. But that is really fancy chemistry. And I'll bet that for a novice, it may not work the first time if you're not used to doing that kind of chemistry. So yeah, there is a way to do it. Yeah, that's not the easiest way. Okay, Sylvia.
Yeah, sorry, one more.
No, there is no limit. Well, my
Okay,
voice will do
for-
that at some point.
So for acetals, are you going to tell us if we're removing water explicitly, or are we supposed to assume we're removing water?
No. Wait and see the question. I think it's clear enough. I've asked it before, and for those that get it, there are no issues.
Okay.
For a large percentage of students, they did okay.
Okay, so on the recitation, like when you write reflux, that means you're not getting rid of water, right?
Uh, you know, on an exam, I would hope I'd be a little bit more careful, but in general, you have to go by context. You don't need the heat to make the hemiacetal, and making the hemiacetal is usually not a useful thing to do because it's not stable. So unless the hemiacetal somehow makes sense in contacts, it's probably the acetal that's wanted. That's the thing you intentionally make. The hemiacetal is just the intermediate. There's only those rare cases where the hemiacetal is stable and can be isolated.
Okay, thank you.
Yeah. Somebody in the chat, let me see, wants to know about reducing nitro groups. If you see a metal and a little acid, assume it reduces it. I'm not going to try to trick you by showing you the wrong metal. Lots and lots of metals will do it. One of my favorites is tin-2 chloride because it's a very mild method and it's easy to write. SnCl2. Stannous chloride for those that like the old fashioned. The Sandmeyer reactions are certainly a possibility. I'm not eliminating any reactions from the exam. I'm just trying to trim out some of the side stuff. So there are a lot of reactions, and if you know them, you're not going to have any real surprises. My intent is to get better scores out of you this time. So I've tried to avoid the what the heck is this question. Exam 1 contains basic Orgo as well as specific topics. And so there could be some overlap in this exam and exam 1, but nothing by intent. I mean, it's cumulative, right? Okay, Will again.
All right. On slide, hold on one sec. Slide 39.
Which
ketones.
chapter?
Ketones.
Okay. Slide
Yeah,
which?
39. It's about amine formation if the number's wrong. Yeah, so on the equilibrium on the top right, what's going on? It's switching between
Yeah,
between
that is just a note in passing.
Mm-hmm.
Yeah, it's for the sake of completeness. But if you have a regular amine,
Yeah.
and it has methyl, ethyl, and hydrogen will do, it is potentially chiral,
Mm-hmm.
but it inverts. So you can't isolate them.
Right.
It's the same thing here.
Same
This
thing.
just
Okay.
flips over, the lone pair goes through, that's it.
Cool. Thank
So
you.
this thing just kind of wags back and forth, probably fairly rapidly. But you see the two compounds in the NMR. So the NMR usually has a lot of peaks doubled, which is a pain in the butt. Rua again. We got the same cast.
For the Wolff-Kishner reduction, I tried to draw out the mechanism for forming the final product, but I couldn't really figure it out. I don't know if we need to know the full mechanism, but I'm not sure if I don't think I did it right.
Anybody know the slide for that?
I think it was 16.
16, there it is. Yep, you got it. And this is really the mechanism, but the tautomerization, you need to know. So you're in strong base. So you simply deprotonate the NH out here and put the H on back here. It's just deprotonation, reprotonation, a different spot. That's all how all tautomerizations work in base. And the rest is shown here. I'm not showing the source of the acid, but the solvent, ethylene glycol. You got a protic solvent that would protonate that faster than a shot.
Okay, thank you.
Okay, and we've got a chat question. If you'll let me get to that. No. Here it is. Okay, this is Miss Beckford. So the two of them, I can't explain why, but the aldehyde and the ylide start out their interaction crossed over like this. It somehow involves the d orbitals on the phosphorus, making this possible. So if you just accept that they start this way, you have more than one way to line it up. You can have the phosphorus on the left or right. You can have the hydrogen up or down. So there's 4 ways to think about it. The triphenylphosphine is big, bulky. It's just a huge ball out there. And it does not like being near this carbon. It wants to be near this hydrogen. Okay, so now you have to go to the other side and decide you want methyl up or methyl down. Well, methyl up conflicts with this CH2, so hydrogen fits there better. So it's 2 steric interactions you're minimizing. The steric interaction of the phosphorus and its 3 phenyl groups by pairing it up with the hydrogen of the aldehyde. And then the other side, pairing up the alkyl group of the aldehyde with a hydrogen. When you do that, and then just rotate this up and rotate this down, the dotted lines are the way it's going to flatten out. This hydrogen is going to swing around and match up with this hydrogen. The methyl is going to follow and match up with this phenyl group. And for the methyl or benzyl group, the methyl and the benzyl end up cis like that. Okay.
I have a quick question about this reaction too. In the book, there's a bunch of stuff about electron withdrawing groups and how it affects that. I know you said some of the book stuff on this reaction was wrong. Should we ignore that or?
This is the mistake. The rest is fine.
Okay.
They said that phenyl gives trans now, and it doesn't. Not under standard
Gotcha.
conditions, not in the literature.
Mm-hmm.
Again, I put a disclaimer at the bottom of the slide because, maybe they have a reference where it does switch, but that's just not the standard thing.
Okay.
And so, a phenyl doesn't stabilize a negative charge anywhere like an ester does. Esters are much, much better. Okay, Gregory again.
Will there be 23 product reagent questions?
Yeah, I think that's the number. There's a lot. It's not unusual on my exams. It's worth, I showed the point totals. That one. It is. So there's 150 points that aren't simple reactions, that is simply give the product, not that the reaction's simple, and 180. So it's a little over half. And the numbers here got kind of big just so I could weight this different sections the way I wanted to. So the numbers have nothing to do. Those are relative. I could have made it 6, 18, and 9 and graded it. I just don't like putting down fractions or decimals for partial credit. So the size of the numbers is nothing but a convenience. It'll end up 100 points possible at the end. Seven. Is this the slide you're asking about, Neha? You're talking about my text? There might be a typo in my text. Oh, acylation. Oh, that's yeah, what that's referring to is if you chlorinate this aniline, you're going to have a little trouble stopping it from putting in 2 chlorines because it's so reactive. So this is a reference back to the fact that anilines are really hard to work with in this chemistry. So generally we make the amide, then do the electrophilic aromatic substitution, and then take off the amide. So that's a reference to that. So for the future, I can add a comment here. There. So now there's a parenthetical to explain that for the future. Rua again. Somebody came prepared. Like three or four of you.
I just had another question for this same slide. Should we, well, not this slide, but in general for anilines, should we always assume that it's going to be in monohalogenation conditions because they're so reactive?
Yeah, I mean, if I give you a reaction for that's electrophilic aromatic substitution, I say nothing. You just write me the product that would normally be made, right? The mono alkylation. If you want to be careful, just write in parentheses plus polyalkylation or dialkylation. You know, showing me you're aware of it is fine. But a question may be worded in such a way to bias your answer. I've put, you know, excess benzene, methylated, you get monomethylation. That's the reason you use excess. Or I may ask for minor products as well sometimes. You know, I might say, show me the major and the most expected minor product.
Okay, thank you.
Yeah, I'm looking for a little bit more than just memorization. Sometimes my questions that you may not like as much are looking for a little bit of understanding to go with an answer. Next question. Anybody? Don't wait for others to ask your question. My advice is to make an absolute fool of yourself asking a really stupid question and get a better score on the exam. No, I'm exaggerated. We'll call them naive questions because that's exactly what they would be.
I got a
Clownfish, who's
question.
that? Joanna.
Yeah, can I go first? Yeah. I have a question about basicity in terms of just identifying basicity. I think it's a little bit hard for amines. And specifically there's specifically like with resonance, and I want to clarify some rules about resonance.
Okay, well, let me just step through the amine slides and stop whenever that comes up. Sound good?
Yes.
So the first thing you know about amines is they're a lot like ammonia. They're weak bases in water. So you may get, excuse me. I abused my stomach yesterday at the farewell party for my mother-in-law who's leaving on Wednesday. The whole family got together for a lot of. So anyway, it just partially gets protonated, just like acetic acid partially donates a proton. So that's the water part of it. HCl is a strong acid, so complete protonation. Phosphoric acid is a moderately strong, not strong. You get complete protonation. The last one here is the one that students struggle with. And it has to do with the definition of what a weak base or a weak acid is. Weak base or weak acid is versus water. If you do a pairing where it's either a much better acid or much better base than water, yeah, now you got something. So an amine and a carboxylic acid are, for all practical purposes, completely ionic. Yeah, hold that question, Ethan. It's better conjugated. The conjugation isn't as good because of steric hindrance. Well, we can get back to that though if you want. And this is just encouraging you to put what we learn anytime we learn about acids, bases in context. So amines, this is showing some of the problem. We cite a pKa for an amine. We mean the ammonium cation. Okay. So the pKa's, phenols, thiols, and protonated amines have about the same pKa. Okay. And they're, kind of roughly in between the things you see here. So, just having a rough ranking. Okay. The nitrogen in a pyridine is less basic because it's sp squared. The lone pair is out to the side of the ring, so it's not involved in aromaticity. Okay. Anilines are less basic. My answer is because of the electronegativity of the system it's attached to, but there's also a resonance explanation you can offer. And then both of these have about the same acidity as acetic acid, whereas a protonated regular amine would be a much stronger acid. This is talking to the double meaning of pKa of an amine. The normal pKa of aniline would be 5, but that's for the protonated form. The literal pKa of aniline is 27, which you can't do in water. And the same thing with nitroaniline. Okay, so you got to know what pKa is normally cited and which one you want. And finding the less common one, it can be a pain in the butt. Okay, this is just a passing slide, but you guys are physiological systems. In your blood, amines are mostly protonated because it's a buffered system. It's different than just pure water. Okay. there's a trend from primary to secondary tertiary means to basicity. I've ignored it. Okay, so. And I hope you remember this one. Quaternary nitrogens are not basic, but their counterions certainly can be. So this is just a thinking question. Okay, there's a specific slide. Is it here in the previous chapter? Well, let's go back. Okay. So piperidine would have a normal pKa, pyrimidine. Each nitrogen would be roughly like pyridine because they play the same role. Pyrrole is not acidic. It's not a base. It's not base. You have to dissolve it in pure sulfuric acid to even protonate it. So in water, it is not a base, period, because a lone pair is part of the 6-electron aromatic ring. So if you look at imidazole, which one looks like pyrrole? Well, this one does. No double bonds, and it has a hydrogen on it. And then this nitrogen now is a little bit more like pyridine. So it can be protonated. The proton comes from the side. But when you protonate it, this lone pair can resonate. So both nitrogens help the positive charge. So it's a little bit more basic. Okay, so that's the one that's more tricky.
Could you explain that one more time
Which
about
part of it?
the
All of it?
second nitrogen? So you said that
Okay,
one.
let me take it to ChemDraw so I can show what I'm talking about.
Mhm.
Okay, it is strange. I've always thought it's strange. So if you think it's strange, join the club. So you protonate it, and you have the positive charge, and so far we're talking pyridine. But there's a resonance structure can push the arrows if we want to. We've put the double bond down here. This arrow neutralizes that positive charge, but it's down here now. And now the two nitrogens have traded roles, which is strange. You've got an aromatic ring, but when it's protonated, there's resonance that's kind of independent of it. It's, you know, it's a strange thing. Okay, so that
Get it.
is the resonance that makes that a more stable cation. Joanna.
I'm still a little bit confused about the idea of stability. So when you talk about the idea of stability, stabilizing a compound such as this, the one that you're showing, it's from like the resonance. Is that like an example of how it is more stable than the other compound with the one less nitrogen in it?
Well, if you don't have, if you just have one nitrogen in like, it has to be in pyridine. You know, this certainly can be protonated. I mean, PCC, the reagent for oxidation, has pyridinium in it. This is pyridinium, okay? So there is no resonance structure here that helps carry that positive charge. But in a 5-member ring, in imidazole specifically, that does exist. And I'm sorry, I don't remember the name of this beast. It's not that common. If you protonate here, and this is exploring for me. I don't know the answer right off. So is that nitrogen more basic? Well, this lone pair can go here, here, here. Yeah, there's a resin structure with a positive charge on the other nitrogen. So it works here too. So here's another example. That'd be a great test question if I needed an additionally challenging one, but not today, not this semester. Yeah, again, that's not a common compound. That sounds familiar name. We'll get rid of that. Yeah, Jessica, you have a question about weak activating and deactivating groups. If I wanted to give me more than just the one determined by the better activating group, I would make a leading question out of it. Yeah, if for those that aren't following, a leading question is one where I give you hints. I kind of guide you. So where was that question? Yeah, if you take, this is for Ethan who asked a good question. If you take orthoaniline and draw the resonance structure with a lone pair on the aniline nitrogen, is pushed all the way through to the nitro group. Now both nitrogens are planar, and there's a steric interaction here that diminishes the contribution of that. The pictures don't do it justice, which is why I color-coded these things. So, it's just a curious thing. There's a steric interaction here if they're both force flat, which the resonance structure does. Oops. Yeah, it's not very well focused, but you can see it glittering. They're very pretty crystals. I remember some of the labs I did when I was your age better than I remember what I had for breakfast yesterday. If I presented a mechanism, it is a possibility on the exam, but let's go back to the slide. I want your reaction intermediate, that doesn't not a resonance mechanism per se. Resonance structures show a complete mechanism related to acetal. So I'm not asking for any complete mechanisms other than that one. But you might want to learn the others because we have one more exam and especially a final, and who knows what's going to show up on the final. I'm not going to try to be mean, but I want you to have knowledge of those. So you got spring break, right? Yeah, I know. You all want to enjoy your spring break. Spring break's for catching up. You know that, right? It's for saving your butt. It's for writing your term paper you haven't started yet. Gregory again.
Yeah, I got a question written out that I want to ask you about.
Yeah, you want to hold it up?
Yep. So the question is,
Hold it closer. Okay, so yeah, I can see it now.
why is BR the one that's being changed and not CL
Oh, where'd you get that question?
online?
Nitro group stabilize the negative charge much better than nitriles.
Nitro group stabilizes
Yeah, a
the
nitro is the best group to take up to resonate to stabilize an anion. Nitriles do it, but they're not that good at it. Nitro compounds are fabulous at it.
Wait, can you hold up the problem again real quick?
Yeah, you got to talk, Gregor. You got to talk to come up on my screen anyway.
Thanks. Now I see it. Thank you.
Oh, you
Okay.
can see it. I can't.
I had to zoom in on his pick.
Would you be able to draw the resonance structure that explains the what you have said?
Yeah.
Thanks.
Okay, so if you add in a nucleophile, so it was methoxy, right?
Yes.
So the negative charge is, I should have redrawn it, but hey. Okay, so that's the resonance structure for the nitro.
So it's not an SN2 reaction.
It's an addition elimination. It's sp squared carbons.
sp squared carbons mean there is no SN2.
There is no such thing. Okay, so that's the comparison. So on the right, you have an sp squared nitrogen carrying the negative charge in this one resonance structure. That's not that good. I mean, yeah, it's a benefit. You got, a more electronegative atom helping out. It's part of it. But here, this is a very good grouping. These oxygens are actually sp squared. They have to be if there's going to be resonance. And the nitrogen, so you got 3 electronegative atoms here. The positive and the negative kind of complement each other, so that's not a huge deal. That's present in the regular nitro. And then oxygen, you can't beat a nitro group. It's one of the absolute best for stabilizing anions. The question is a little bit of a tease because the chloride is the more reactive halogen than the bromine, all other things being equal. But these carbons know the nitrile, the nitro group are out there.
Can I say something?
Absolutely.
I thought that the reason for Br changing for methoxy group and not chlorine was because a nitrogen group, which I'm talking about N00, it's the strongest deactivator and it's in meta position.
You're thinking different chemistry. You've got to set your mind to the kind of chemistry you're looking at. So the consideration here is an anion attack. You're not talking about positive charges like an electrophilic aromatic substitution. You're talking about stabilizing a negative charge. So you got to think that way. So you've got to realize when you attack with a bromine it's the nitro group that's paired to that and can take up that negative charge in resonance. If you attack with a chlorine then it's the nitrile that takes up that in the resonance structure. So totally different thinking than electrophilic aromatic substitution.
So
Okay?
then, yes. So then once we add a methoxy group, we're gonna have a shift of bonds from here to here, and then a shift from here to here. So from here to here.
I'm not sure what you're talking about. You're talking about the next step or?
Well, starting from from the original
The
material.
original structure's at the bottom here, so mark that one up.
Yeah, okay.
But I've shown you where the bonds end up.
Let me try to ask in a different way. Once we join the methoxy group to Br, we're shifting the double bond that was present there, which is not really a double bond.
Yeah.
So it's gonna go. I think the double bonds at the bottom, they're structured in a different way, not like the original question. So
Well, no, that doesn't matter.
that doesn't matter.
No, there's 2 ways to draw that, and both of them are equally correct. They're resonance.
Okay. All right.
That's-
So then this one will go here, and then it will shift this one over here. Is that how it will happen? After
Well, yeah, that's how you show the resonance structures. There's no reason you can't add the methoxy and show the negative charge here. That's a valid resonance structure. It just doesn't explain the role of the electron withdrawing substituents.
I think I got it. Thank you.
Okay, I've put the red here to show you the charges and help see it a little faster. That's where the negative charges end up. Okay, it's a cute little question. Last exam. Okay, well, let me bring that up. Oops, missed. Okay, question 16. If you show stereochemistry, that's fine. Yeah, I probably should for your benefit, but you have a 5-member ring and a 5-member ring. You can always assume those are cis. Yeah, I mean, for a complete answer, you probably should. But I'm more interested if you were in lecture and learned the nature of cyclopentadiene. I mean, the point is, it does a dimerization spontaneously. If you know that, I'm happy. But it's a good question. Okay, I have another question here about direct alkylation making primary amines. And other choices. Choice is dependent on many things. If you had a very expensive alkyl chloride with a fancy piece out there, you're going to use whatever reaction gives you the highest yield without any concern about convenience. I mean, you'll go through a lot more work to preserve what you have. If you're making it with a very simple amine, yeah, you can use ammonia in commercially. It's also a question of scale. Some reactions you use on a very small scale, but when they get very large, you end up with problems. So then you have to switch to a different method. It's a complicated question, actually. Joanna again.
I'm so sorry. Can
No,
you hear me?
please, please. Everybody appreciates you asking questions.
I really am so confused about number 14 on the homework for chapter 22 amines. I am so confused about specifically the difference in like
Okay, the means
when
homework. Let me get there
ranking
one thing at a time. Which question?
number 14.
14.
Yes.
Yeah,
Specifically in
well,
the ranking of
this
2 and
is way
7.
too this is way too much to go into exam.
Oh, okay, that wouldn't be on exam.
But you know, it's great for thinking. Right? So
Yeah.
if you can think through a question like this, you know you're ready for the exam. Right? That's kind of the point. So the normal amine is most basic. It's hard to make that nitrogen more basic with any modification, although there are ways to do it outside of aromatic systems, but and then we know that this has increased, is left basic, but is a good one. We know this one is non-basic completely. And so these 3, I think, are okay. Going to the left. The aniline, I don't have the pyridine here, but it'd be the same as the aniline. 3 has an electron donating group. Alkyl groups are electron donating relative to a ring, and that would slightly increase the basicity of this because it has more electron density. So 1, 2, 3, 4 being the aniline itself. 5 is a nitro group. It's pulling electron density out of the nitrogen, and that makes it less basic. Still basic, it just reduces it. But it's purely an inductive effect because it's meta. 6 is para-nitro. That is a strong resonance between the lone pair of nitrogen and the nitro group. That is not a very basic amine at all. The only one that's less basic is 7, which is not a basic. So does that help at all?
Yeah, that helps a lot. Thank you so much. I was so confused.
You know, this is 3/4 of the way through a second semester of organic chemistry. And some students are up to this type of question, but I would say the majority are going to struggle with it. You know, my homeworks are written to make you think.
So, excuse me, Professor, you said that number 5 is the only reason that N2O is its induction effect.
Yeah, it's induction. The lone pair of nitrogen can't resonate with that nitro group.
Okay, got it. And if it would resonate, could you show how it would do it on the para? And why would their resonance be in the first place? Like we add something, or does it just
No, spontaneously.
spontaneous? Okay.
Okay, that's a good question because it let me proceed. Yeah, I took out the 1. Okay, well, I'll let you add the arrows.
You saying you'll let me add the
Yeah,
arrow?
I'm going to add the structure and you can add the arrows to get there.
What an honor. Thank you.
Hey, I
Oh.
can't do all the work for you.
Okay.
The things you figure out by yourself, you learn better. And then we just need the charges. Okay, so if you want to know why the nitrogen is less basic, this is the resonance structure you draw. Okay, and I'm sure you can figure out the arrows if you just put it down and play with it. If you want to know about the acidity of this compound, that's a different question. You know, this answers the basicity question. You need to draw that anion and then show the same resonance, which is trivial to draw from what I have. So this resonance structure of the neutral aniline tells me it's less basic because the lone pair is getting sucked down to the nitro group. The anion now is more stable. That is, this is more acidic because the conjugate base has a great resonance structure. They're closely related for questions, but the answer is different. Brandon, I think the answer keys are posted, aren't they? I think they posted at noon yesterday. So check it out. If you don't find them, send me an email. Anything else? Okay, I'm just going to annotate this. Okay, so that's kind of putting everything down. The top, if you want to know about basicity, you want to know how available lone pair is, and the answer is the nitro group is reducing it. At the bottom, you want to know how acidic it is. So you make the anion, and you show that the NO2 makes, I should reword that. There we go. That keeps the thoughts clear. The nitro group is making the negative charge more stable. I think I liked it better the other way. Okay, well, people are bailing, but Joanna, you got another question?
Yeah, I have a question on specifically chapter 19 on slide number 36.
Okay, which chapter?
Chapter 19.
19. Yeah, I don't know them well by number, actually, but they're
It's
labeled.
the aldehyde and
Yep,
ketones.
which slide?
Slide 36. And it's just specifically the third one, and I was going over it, but I am having a hard time understanding why the second step is favored by entropy. Is it because of the
Let me draw a
like
structure for you. I think it'll make it clear. Yeah, I want
okay.
to export this before I'm done. This is something that might be good for a slide someday. Export. I don't do this very often. And I don't want PDF. Oops, I gotta rename it. And I can't modify this, but doesn't matter. Okay, the first step is just an alcohol finding a ketone. It's like that second OH isn't there. Oops, I left out an oxygen. Okay, so you're at this point, you're gonna protonate this oxygen, lose water, and get to the intermediate. And just, oh, that's not what I wanted. I hate it when it does that. There we go. So let's say we have a little methanol around, not really a solvent, and we have this as the intermediate. Which one has the advantage in finding that carbon? This one or this one? Which one can win the race to close the ring?
Yeah, the first one, the one on
That's
the
the
ring.
entropic advantage. Okay, so I've talked about it being, if you were using methanol here, you'd have two methanols in the ketone, 3 molecules making 1. So that's a loss of entropy. The way it is shown, you have 2 molecules making 1. That's a loss of entropy, but less. But this is the other way of looking at it. You know, who's got the advantage in making that ring? And intramolecular, you lose less entropy. It's got a better chance of making the ring. That's kind of the thinking you need to have. Okay, so hopefully that helps you think about it.
Thank you.
Slide 37, is that on this set? Yeah, someone sent me a direct message about slide 37. I don't know if it's a... So someone has a question about this slide? Okay, we're coming up on, oh, the next slide. This reaction? Oh, the mic's not working. Okay, well, this is an amine, and formalin is a substitute for formaldehyde. You can just, if I ask for a mechanism of this, you can use formaldehyde. Okay, so the formaldehyde makes the imine here, the iminium salt, and that gets reduced. Oops. It's like here, but without the phenyl group, with the hydrogen here. Then you'd be adding a methyl to this nitrogen.
Could you explain the way that reaction is done, the one that you were just talking about, formalin?
You mean in practice?
I don't understand what do you mean in practice.
This reaction?
Yeah, like how we end up with CH3 and what role does acid
Okay.
plays in.
Okay, so go back to the previous slide. Oh, look straight above.
Yeah.
This is just this with 2 hydrogens instead of 2 methyls.
Two
Okay.
hydrogen. Oh,
Yeah,
okay.
so it's a reductive alkylation. A reductive alkylation puts an aldehyde or a ketone together with an amine, and you make an amine. And the mechanism is here, although, you know, I used allylamine here. Don't be afraid of the stuff that goes along for the ride. So this is going to make the imine, right? You react carbonyl compound or aldehydes and ketones with amines, you can make imines. And this is showing the step-by-step procedure. Again, for formalin or formaldehyde, you'd simply have 2 H's here, you wouldn't have the phenyl group, okay? But then it's got a little bit of acid there, and it has to be protonated for the final step. When it's protonated, this carbon is now reactive enough that even cyanoboryl hydride is capable of reducing it. Cyanoboryl hydride will not reduce an aldehyde, it's too weak. But a protonated imine, yeah, it'll reduce. Okay? Okay, 64 here. Okay, this is Brandon's question. Yeah, this is a fancier way to make benzene. And if you have nothing else in there, you're going to get garbage. It's going to find something to do really fast. But if you have a Diels-Alder acceptor here, this is not a great Diels-Alder receptor. It's not terribly reactive as a diene. It's aromatic itself. But the benzene doesn't care. It's gonna force the game. It's gonna force it to react, and you can make these things. Um, 40. Okay, another good question from Ethan. So you react with ConHCl here. It's partly about relative rates. Nitriles are fairly reactive with acid, and you can end up with this. But one reason this doesn't react is the influence of the electron withdrawing nitrile and carboxylic acid and everything in between. It diminishes the reactivity of this carbon-oxygen bond. You can't put a cation there. You can't see that as secondary because you got a cyanide. That's not secondary, that's an electron withdrawing group. But even SN2 won't work well. Just, you know, I'm not sure a quick explanation for something to me that I'm so used to. Yeah, alpha hydroxy carboxylic acids, nitriles are not normal alcohols. So if that helps you remember it, it works for me. That is the simple answer. So the CN, the nitrile, is an electron withdrawing group, and so is the amide you're going to make in the first step, and so is the carboxylic acid. In fact, the conditions here, if it doesn't make the chloride, would do elimination, but for that. This is a very hard elimination because of that same effect. It's hard to get this to eliminate. This is forcing conditions to do an elimination. You know, usually don't have to heat it up much. Okay, anything else?
Earlier I asked about amides. So for an aniline, when we want to do an electrophilic aromatic substitution, for example, like a sulfonation or something, we put the acid anhydride to turn it into an amide, and that I
Yeah, if
understand.
most of these, any acylation reaction and, adding a sulfonic acid residue to the ring would add it to the nitrogen. The lone pair of the nitrogen is too reactive. Halogenation is about the only one you can really get away with for aniline itself. So it's somewhat limited. That's why we like to make amides out of them.
Right, but my question is, how do you then take the amide and put it back to an aniline? Because
Well,
I'm not.
because of the aromatic ring, because it's an aniline, those are easier to hydrolyze. So it's just hydrolysis. You
Oh,
just heat it up with aqueous acid or base.
okay.
Well, I wouldn't say the basicity of the nitrogen. The nitrogen of a nitrile is sp, not very basic. I mean, it does get protonated in the course of this reaction, but it's not really that basic. But yeah, it's the fastest reaction that happens. Learning an appreciation of relative rates and what reaction wins is not exactly a beginner thing, but here's a basis for developing those instincts. Anything else? Okay, everybody get a good night's sleep and leave the anxieties at home.